Okay, welcome back from the break, and we continue with the work of Florian Pollitt about the deterministic scheduling.
Yes, thank you. So this is kind of a topic change where I'm doing set solving, might be counted as automated reasoning, but this talk is not about proof logging, so it's kind of different than the other talks we saw yesterday and today. So let's start with the CDCL algorithm. This is a very high-level overview. You start with the formula. You might do some pre-processing, and you enter the main loop where you propagate, you learn clauses, maybe you have sub or unsub. And then we have all the interesting ingredients that make CDCL more powerful than DPLL. So first we can restart if we get stuck in a search space. We can forget learned clauses. And then we can employ more heuristics, which is this line 8. So have this mode switching, which changes heuristics in the solver. And then we can do lots and lots of different in-processing techniques. And now the problem I want to discuss today is kind of these things here, they have to be scheduled, right? So we want to know when to change heuristics, or when to, or how much in processing to do. And this is what I'm talking about now. So let's first talk about mode switching. This is an idea by Chansek Ho from 2015. It's kind of, the idea is motivated by observation that the solver behaves, or satisfiable and unsatisfiable instances behave very differently. So why not bake a portfolio into the solver which targets both separately? So we have mainly decision heuristic and a restart frequency, which changes. So for satisfiable instances, we expect to find a model. So we want to have a large trail. We want to have many assignments that are hopefully correct. And then we don't want to destroy this by restarting. And also the decision heuristic for many unsatisfiable instances tries to focus on the newest conflicts, whereas for satisfiable instances, this is maybe less important. So as I said, we're kind of more aggressive, and actually, so we don't call it we call it unstable and stable, and we're more aggressive in this unstable mode, and this leads to slower conflict frequency because we're constantly restarting and building back the trail at low decision levels, which costs more time. And in any case, there's a high variance. So if we now take this idea of mode switching and we say, okay, let's schedule this with conflicts. Let's say we're doing 1,000 conflicts of stable mode and then 1,000 conflicts of unstable mode, and then switch back and forth, maybe increase the intervals. We have a high variance in terms of time spent in these two modes. So maybe for some instances, we'll spend almost no time in stable or unstable, the other way around, right? And this is what we thought we don't want, right? We want both sets of heuristics to work same amount of time. We're not trying to predict whether this benchmark is going to be satisfiable or unsatisfiable. We just want to kind of throw both heuristics at it and see what happens. So how are we going to get a time-based schedule? And here, the very important point is like reproducibility. I'm sure many of you that develop solvers know if you want to debug something, you really want to be reproducible in your results. Don't want to have a segfault on the cluster and then on your machine you can't reproduce this. Yeah. And also for similar reasons, we don't want to be hardware or operating system dependent. So we really want something that works the same on any machine. And our solution is just counting. So very basic, but what are we counting? And we're counting ticks, which it tries to count cache line accesses. So it's not an exact solution, it's approximate, and it focuses on the hotspots. We're not guaranteeing like that this will always be 100% accurate. We just want to be better than like these metrics that are otherwise used, like conflicts or propagations. We want to have a more closely related metric to time. And well, why count cache lines? Because we know SAT solving is kind of memory bound. And so Knuth has this idea of MEMS where you measure the running time of an algorithm by the number of memory accesses, and takes this kind of a refinement which maps more closely to modern hardware, where we say, okay, actually not every memory access is expensive, just loading new cache lines is expensive, and that's why we kind of count cache lines instead. And then we apply this. So for our first, like for this mode switching, we have to apply this to our hotspots, which are propagation and maybe also clause learning. And once we do that, we can use the computed ticks to schedule. Now, I have another pseudocode slide.
So cache lines are not always the same size, right? So it means that you might have different counts on different computers.
Yes, so this is true. And actually, we're just assuming a constant here. So we're really favoring the determinism over anything else, right? So I think this is might be 256. I'm not sure this constant is correct, but it's like either this or 256, and we just hard code it. Right, so you probably have seen a propagation routine, but this is very close to what's actually used in KISAT. If you abstract away like all the low-level C code. So we first have to access our watches, and we already know we iterate through the entire thing. So we just compute the cache lines based on the size of this watcher struct and the size of the watch stack. Right, and then maybe we can skip the clause because of the blocking literal. Otherwise, like this is the main hotspot, first dereference of the clause. And then our free cases is assigning or changing the watch, or then a conflict. And this is already, or here in this already breaks kind of our first assumption that we're always iterating through this entire thing. So yeah, this approximation might not be 100% nice here. If we get many conflicts, we might not iterate through this. Yeah. And then once we have all the ticks, we just increment the current, like either stable or unstable counter. And now when we schedule the thing, we can say, okay, let's have stable mode always use the same ticks as unstable mode. And to get a first get a first count of how many ticks we want to schedule, actually, we run one of the phases in with conflicts. We say, okay, unstable is always first, then it will run with conflicts, like 1000 conflicts, and then stable will get the number of ticks that unstable used. And that way we get a more close approximation. Yeah, and this is the results. If we apply the ticks to this mode switching, so we have two versions of Cadical, and the only difference is this scheduling. In each point in this plot is one instance of this anniversary track, and it just plots the ratio between unstable and stable mode time. And you can see there is a wide spread with the default scheduling, and then more more condensed spread with tick scheduling. We still have some outliers here, like especially at the very beginning, which is kind of expected, because this in the beginning the solver is still doing variable elimination and other in-processing things very frequently, and this might actually change the cost of stuff. If you manage to eliminate half of the variables here, then maybe your tick counts would also change, but this is not really taken into account. So you would expect a bigger spread at the beginning. As you can see, like this skew towards unstable, so above 50% is more unstable, and below it's more stable. So the skew towards unstable can also be nicely observed. So this is the median line, and this would be a perfect balance. Yeah. Right. So now we're happy. We have managed to improve this picture. We could think about how to improve this more, but let's first look at actually, like, finally we're not interested in improving this picture, right? We're interested in improving solver performance. So let's look at the solver performance, and actually it decreases slightly. Yeah, so on this benchmark set, we're using like 60 instances, and from the CDF, you can also see that there's a gap between the two. So the old version really is a little bit faster on these instances. That's not very reassuring. And there are some ideas of what could be the reason for that, but still kind of ongoing work. So maybe one of my ideas is kind of that this skew, and I think also Matthias had confirmed, no, I think mentioned something else. Okay, so one of my ideas was that, okay, maybe we actually want to have more unstable mode. So decreasing this, like the blue line, it's actually kind of bad. And this is, I started doing some cluster runs where I play around with this expected ratio here, and maybe this will get some results, but I don't have results yet. So this is one idea. Another idea is maybe actually we think we want to use both heuristics same amount of time. Maybe that's not true. Maybe there are benchmark characteristics that actually tell us, okay, you use this heuristic or you use this heuristic. And by using tick schedule instead of conflict schedule, we're discarding at least one of this kind of benchmark characteristics, which is just a conflict frequency, right? So this could also be like a reason, which would make us really sad, because it would mean that the entire idea of using ticks instead is kind of flawed. But yes, even if that's the case, we have another application where ticks are really useful, and in processing. So generally in CDCL in processing, because you can restart the CDCL algorithm at any time, you're really free to do anything to the formula at any time during the search. And that's why there are so many different in-processing techniques, and new ones get proposed all the time. But we never want to get stuck at our in-processing, because we know CDCL works, and if we have this new fancy technique now, maybe it helps, but we know if we spend 100% time on it, it won't help. So how to avoid getting stuck at our new fancy in-processing technique? Well, we correlate it with solving time. So we just say, if we spend at most 10% of our time in this thing, it will help, or that's the hope. So we fix some fraction up front, can expose this as an option as well. And then we just run our thing for this amount of ticks. And here it's really useful that actually we have something which more closely relates to solving time, instead of like using conflicts or propagations, where we know there's a wider spread and there might be outliers, where actually if we just schedule vivification based on propagation, maybe vivification does employ propagation during its routine, but maybe the propagation in vivification is actually a lot more expensive, because it's always performed at low decision levels, and in the search we're doing it at high decision levels. So we always have these kind of issues, and right, using ticks we can mitigate some of that. So yes, we can apply ticks to the scheduling of all of our fancy in processing techniques. But well, this is kind of a negative slide. So how do you do that? As I said before, you add the ticks to the hotspots. This is the most important part. Then I can't tell you what the hotspots are. So you do some profiling to figure out. You add some ticks to your hotspots. You run again, start scheduling your algorithm based on this, or you just check whether your counts correlate with the running time of the algorithm. So you do some more profiling and maybe you refine. You can, if you already schedule it, you can have a target time. Otherwise, you would have a kind of target count. Yes, you can do it both ways if you have an alternative schedule. And yes, so this, if you want to apply this idea to your own solver, then unfortunately I can't tell you anything better than, well, you have to spend a lot of CPU time and hours of your time to be able to get a close correlation, solving time and tick count. Right, and before I go to the conclusion, because I have a little bit more time, I can tell one more story about this vivification. So when we started integrating ticks into vivification in Cadical, we actually observed that sometimes we have really big outliers, and actually already the initialization of this algorithm took way too much time. So you have another issue where actually before you even start doing anything useful, you run out of time in your algorithm. So you have to take this into account when scheduling. So maybe you want to delay vivification when you have not accumulated enough ticks to even run it and stuff like that. So it's really finicky with the scheduling. Yeah. Yes.
Maybe you can show on the plot you have the walk point.
Right.
Because it's also interesting because you have to look at the special cases, right? So you have to identify special cases.
Yes. Well, part of this is identifying the outliers, and what I didn't tell you in this plot is actually timeouts are marked with X's. And then you can see, okay, we have a 2,500 second timeout overall. Actually, the X's are not at 2,500. Why not? Well, this plot only shows the time spent in search. So it will not show time spent in processing. And then we get outliers like this one, where the solver times out without doing any search. And why is that? Well, it could be a mem out. I'm not sure if I filtered out mem outs in this plot. I know that so this is a modified version of the original plot where the mem outs were already filtered out. So, but even in the original plots where we didn't have mem outs, we had some of these crosses at like 500 seconds, where actually the solver spends 2,000 seconds doing some in-processing thing. And this, as Matthias mentioned, was not vivification, it was local search in the solver. So if we're not careful, well, we're really getting stuck at these in-processing things. So yeah. So this is my conclusion. We have a mechanism to schedule things inside of the SAT solver, which is more precise than conflicts or propagations. We're kind of disregarding benchmark characteristics. So this is also why maybe if you think, okay, restarting in the solver, why not schedule it with ticks? Well, we want to restart when we're getting stuck in the search space. So we definitely want to look at the current run of the solver and not just say, okay, after 10 seconds, we're definitely stuck. Let's restart then. That doesn't make sense. So maybe you want to take these benchmark characteristics into account. Then the big negative is this, that's a lot of manual effort. Takes lots of CPU time, but it gives a kind of good enough solution. So we're really able to get rid of all of these outliers in this plot. So we're not getting stuck at stuff anymore. And we're also able to decrease the spread. So it kind of works. But also one caveat, if you're doing something upfront, of course you don't have any counts yet, so you can't use this for kind of upfront work for pre-processing, which is also the reason why like the first phase in our mode switching is always based on conflicts instead, because we don't have a tick count yet for this.
Okay, thank you for your talk, Florian. Are there questions? Yes,
I
Matthias.
think the vampire people are counting number of instructions instead of
Machine instructions.
machine
yes.
instructions.
Machine instructions,
which-
yes.
That works only on Intel, and even on Intel, it's not consistent between different processor generations.
Okay,
So this is really a hardware specific thing, which doesn't really work for us, and
that's not what we want at least.
it's not what we want.
In EI count insertions into the term bank. That is fairly linear with time, in my experience. But it's not something that generalizes to
Yes,
subsolvers.
you need to.
New
mean,
terms.
Ticks are also kind of more well specific to subsolvers, because you know that propagation is the most important algorithm, and you know that like this one line in the this line will take 80% of your time. So just counting ticks here would already be a good approximation.
Yeah, but it would work for other things, right? I mean, you might just have to count some ticks otherwise. Just say,
Yes.
okay, here
Yes.
I have
so-
some complicated calculation. It's taking 5 ticks or something.
Yeah.
Okay.
Are there more questions? Maybe you could extend on the difference from Knuth MEMS measure to the ticks.
So he's really counting memory accesses, and he is even stating the complexity of an algorithm in terms of O notation based on this, or just the cost of the run of the algorithm on a specific instance based on this.
This is a very weird combination of super theoretical analysis and super practical assembly code algorithms. And yeah, he's really, but he's doing in theory, not in practice. He doesn't have a mem access counter in his virtual machine, or maybe he has, but not a real machine.
Yes, I mean you could do it in C if you have your own, or even in C++ if you have your own. Well, not that's no for memory allocation you can do it, but for memory
Allocation you can
access,
count, but access not practically.
Yeah.
You can, but the overhead would be incredible.
Yeah, so really, I mean, you need an approximation because you don't want to count everything, and then if you're already doing an approximation, you take one that's maybe even closer to runtime and cache length.
Then let's thank the speaker again.